So we're going to jump right in. I actually met our next keynote speaker when I was putting together the lineup for the original Surge conference a few years ago. I was trying to find someone different from what you see in the typical operations conference lineup, which there's nothing wrong with that. All credit to John Allspaw. But I like to find someone a little, not the Neil is off the wall, so to speak, but so at the time I was just starting to get personally really serious about capacity planning, and I'd stumbled across one of his books, and I thought he would make a great speaker for Surge. So I approached Theo Schlossnagel, and I was like, hey, there's this guy I found on the internet, Dr. Neil Gunther. And Theo's like, and I want to make sure I quote him accurately, something like, fuck yeah, he's fucking brilliant.
Okay, I'm done.
And sure enough, I mean, we were all blown away at Surge, and I knew, the moment I was going to do a monitoring conference that I wanted Neil to join us. So please put your hands together for Dr. Neil.
Thank you for the reception. I am going to do something different, partly because I had no idea what Jason wanted me to do. This is going to work. Worked before. Display. Yeah. It came up before real easy, so there we go. Sorry about that. Okay, so I wasn't sure what Jason wanted me to talk about actually, and my background originally is in theoretical physics, so I tend to live in the world of trying to make something out of data, which is otherwise known as models, because that's kind of what we're trying to do in physics. So when I see data, I'm already thinking of some kind of abstraction. What is this data trying to tell me? Because data is not information. And the models that I work with, you can think of those as transformers. That's the thing that transforms the data into information. So monitoring, of course, is the starting point. Monitoring, I'm referring to collection of data in real time or near real time, the sort of thing I think most of you do. And so what I want to do now in this presentation is throw out some ideas about how to think about data a little bit differently, perhaps from your normal workaday thoughts about these subjects, and also the kind of tools that you use, and also some ideas perhaps for the hacking workshop thing tomorrow. Interesting enough, already I detect some overlap with what John had to say, so that looks like a good sign. I've also got more slides in minutes, so I'm going to have to kind of step through these. Let's get calibrated about data. What do I mean by that? By the way, I don't regard myself as a thought leader. So please don't treat me as a thought leader, because I have a statement about thought leaders. People who follow thought leaders presumably have the intelligence of Orwellian lemmings. I find the term thought leader extremely scary, particularly in this day and age. Orwell must be spinning in his grave. So please don't call me that, and I want you to challenge everything I say. Falsify everything I say if you wish. So, first statement. I have a number of these things which are in my book, and I give in my classes and so forth, called guerrilla mantras, because the classes I teach and the books I've written are called guerrilla something. I stole the idea, it's not original. But I do guerrilla capacity planning as one of my major classes. So, in that class, I talk about the fact that all data is wrong by definition. A statement I think most of you probably haven't heard before. Now, normally in the class, I have fun with this because I ask people to try to think about what the hell am I trying to say here. I don't have time to do all that today, so I'll tell you. So, first thing to realise is that measurement is a process. It's not math. Certainly you see the data represented as numbers, and by the way, that's the only way you know what reality is through those numbers. But the numbers are arrived at but through some kind of process. Do you really understand what that process is? Therefore, all data has errors in it, measurement errors, because it's a process. We're not calculating numbers, we're measuring things, and we're measuring things with essentially some kind of a ruler. It may be electronic or digital, but it's still a ruler. And so there's going to be some discrepancy between the ruler and the thing that you're measuring, and that produces errors. It's always there. The question is, how much error can you tolerate? But it's way worse than that, because you actually, in most of the tools that you use and that you see, have no identification markers to show you that there are errors there at all. So you're kind of travelling under an illusion that this data is somehow divine. Treating data as divine is a sin. For example, most of the monitoring tools that I see around would never get into FIS-Rev A, B, C, or D, because they do not show the degree of error in the data. Here's the bump that corresponds to the Higgs boson, by the way. It's something you've probably read and heard about over the last year or so. The claim is that it's basically been discovered. By the way, Peter Higgs, I know Peter Higgs. Peter Higgs was my PhD examiner. Fortunately, he's still alive. He might get the Nobel Prize next year, we'll see. But there's this bump. And the thing I want to draw your attention to is those little, there's a blow up there in the middle, those little things that look like hand grenades with spikes on them. That's the error bars. And those error bars have to be conformant with the curve that you see there in the ugly green and yellow line. And because that's a 1 and 2 sigma level, to be a legitimate particle in terms of particle physics, it has to be, the data has to be valid up to 5 sigma confidence level. And in general, Higgs does seem to be there. It looks like it has been discovered. It looks real, but it'll take another couple of years to really sort out all of the properties of that thing. So all data is wrong by definition. What I mean by that is that all tools should display or somehow indicate what the level of error is, because it's there. You can't get rid of it. You may minimize it, but it's never zero. If you're not aware of it, then you have no idea what kind of confidence to have in this data. The other thing that I want to touch base on is this thing I call vamoose. Vamoose, your data doubts. What I mean by that. So it's really a cyclical process of visualize, analyze, modelize, over and over until satisfied, and then rinse and repeat. So that's basically the idea. So the tools that you're working with and developing are really a foundation for visualization and analyzing. The modelize, that part probably doesn't exist in a lot of tools. That's the kind of thing I tend to do. That requires a lot of cognitive processing and so on. It's probably not something we're going to be discussing too much in this conference. So I'm going to focus on the V and the A part, the visualize and the analyze part. Now I want to show something else here. I want to show you something from the future. So it doesn't exist. So hopefully this is going to work for me. It's a multimedia presentation. It's not working. I don't know why. Here's some data. Can you see that okay? I think so. Yeah. So imagine this, you're used to seeing endless strip charts, time series. The x-axis is time, the display strip charts. John had some great examples there where they obliterated the entire screen with time series. So think of something like that John showed, but each of those curves, let's suppose, is like a time series. But what I'm really showing here, and what I'm thinking about, is that this would be a way of representing, and look, watch out for patterns, by the way. This could represent an entire data center. In other words, I would like to see performance, which is the thing I live and breathe, or capacity, whatever, as a shape. The hell with strip charts. If I see another strip chart, I'm going to puke. So this is the kind of thing I would like to see. I don't know anybody working on this kind of thing. The commercial tool vendors don't want to work on it because they don't see the ROI. This looks to me like an excellent opportunity for open source. So something to think about. And by the way, I'm going to throw out a lot of these things, and I'm happy to discuss them offline. Obviously, I don't have time to take questions today. So that's the kind of thing I would like to see. Whatever the hell that means, I would like to see something like that available for us, because that gets back to John's point about cognitive processing, which I'll come back to shortly. All right, so back to the talk. So the next point I want to make is that there are only 3 performance metrics. You're either talking about a time, a rate, which is inverse time, or a count, or a number of some kind. technically done. I'm talking about classes of metrics, obviously, but I've given some examples there. But there's a way of cross-checking what you're looking at. All these things, any metric that you come across or like to define has to fall into one of these three camps. Otherwise, it's not legitimate. And I'm not making this up. People make up metrics willy-nilly, which actually make no sense. Google speed does not measure speed at all. So if you'd like to, we can talk about that offline. Watch out for patterns. You may have seen a pattern in that movie I was just showing you a second ago. But watch out, because the brain just loves patterns. So I summarize this by saying that all meaning has a pattern, but not all patterns have a meaning. So you have to watch out. So the cognitive processor, our cognitive processor from an evolutionary point of view is completely built to see things like faces, that we have special circuits for just seeing faces, identifying faces. Sometimes they work. The cognitive processing of the brain is just so eager to look for patterns to make meaning out of something, whether it's really there or not. That's a problem. So you need to give the right visual cues, otherwise you have people charging off in the wrong direction based on the data that's been monitored. All right, so that's a couple of ideas to think about. Now I want to go and do a little potted history of actually performance instrumentation or monitoring, because there's an old adage that says there's nothing new in computer science. So if you go back to the mainframe days, I know you weren't there, nor was I only just read about these things, I'm not that old. Mainframes, actually when they started out, I'm talking about post-World War II, 1950s or so, they didn't need monitoring or instrumentation. The reason is because they were basically doing one thing, batch processing is what we would call it today. So basically crunch through the billing cycle to send out bills so that people send in their checks so that your company survives for another quarter, this kind of stuff. So most mainframes were built around that and didn't do anything else. The way you programmed them was like this, and then eventually things started, the interface began to improve. And then we come to around about mid-1960s, when just across the street here, now that I think about it, a computer system that broke away from that paradigm was developed at MIT called CTSS, Compatible Time Sharing System. And that was developed at the beginning of the 1960s on an IBM mainframe. And the compatibility referred to the fact that they're going to try and throw on the top of what is naturally a batch processing system the idea of interacting with the computer. Because the way you interacted with the computer before that was you do those punch cards and you throw them in a pigeonhole into the bunker, then you come back tomorrow and you get the fan fold and see what happened, and then rinse and repeat, that kind of stuff. But what if you could actually interact with the computer? Interesting idea. So I'm not going to talk about that aspect. What I'm going to talk about is that most people don't know that this was when the first monitoring really began in computer systems, digital electronic computer systems, around about 1965. The CTSS system was eventually genned up to become a multi-user system. So timeshare and multi-user, we're all familiar with that today, and it was called Multics. And in that system, they had the brilliant idea of actually putting some instrumentation into the operating system so that you could tell the responsiveness of the system, because we're now talking about interacting with the system. And I'm just quoting here from the original paper, which says, a rough measure of the response time in this time-sharing console user could be attained if we implemented this formula, is basically what they're saying, into the operating system. And this equation, although it's a bit odd here, is really an iterative form of what's called an exponentially damped moving average, or in modern terminology, a data smoother. And the other thing I want to point out is at the end of the paper they talk about the lessons learned, and they say that basically, hey, this instrumentation idea, that's a good thing, because it's worth the effort. There is some effort in doing the instrumentation, putting it into the system and having it reliable and bug-free, but the payoff is potentially enormous. You know this today as the Linux load average, or load average in Unix if you wish. That's the very first monitoring tool that I'm aware of. Goes all the way back to 1965, because that same code is being used today. That equation is written in the Linux kernel there, right there. lines 67 through 70. And if you want to see all the gore and detail of how all that works, you can look in chapter 4 of my Perl PDQ book. And there's an example as we just see it today. Then we moved to 1970 or so, and the way things traversed then, we had CTSS here at MIT. They then introduced the idea of multi-user interactive system, Multics, which begat Unix at Bell Labs, which later became Unix. Then came screens. By the way, note the mouse in her right hand. Nothing new in computer science. That's about 1968, circa 1968. If you want to see the whiz-bang grandfather of all this, see Doug Engelbart's presentation from 1968 done at the San Francisco computer conference, and they actually televised it from Menlo Park to San Francisco. This is like, you know, multimedia of the day. And you'll see the round screens, and you'll see him using windows. There's no boundaries on the windows, it's just green text, but he's moving them with a mouse. It's well worth looking at. It'll part your hair easily in the middle. The other legacy is that we now have, you know, things like other instrumentation, other ways of representing the data, and we have it today. I can run this on my Mac. In fact, this is a screenshot from there where we have this ugly ASCII green characters on a black background, and this really goes way back to about the 1960s or so, nothing new. I'll come back to that black background in a second. By the way, did you notice the background that John had in his talk? Did anybody notice what colour it was? Pale green. Good choice. John doesn't have any idea why, but it's a very good choice. No, I'm just kidding. So I'll come back to I'll come back to why it's good in a second. And then if we go forward now from this kind of thing, so we still have this today, and I'm not saying that's not useful, it's just that nothing new there, and you know, you have to look at all this stuff in real time because the numbers are changing in top and so forth. The other possibility is that you produce, you know, more endless strip charts, in this case completely coloured spaghetti. So of course time always on the x-axis, and then good luck figuring out what all of that means. You have to go and read the legend and figure out what all these lines are all over the place and try to make something out of that. The brain is extremely bad at trying to make anything out of this, or I should put it around the other way. The brain is extremely good. This kind of representation is extremely bad. So today we have this same kind of thing, endless strip charts, basically time series. This is the load average in a modern rendition circa, you know, a decade ago on the web. This is MRTG type of plot. And this is showing 24 hours, which is fine. That's the window of time we're looking at. And yet, the funny thing is it's showing the 1, 5 and 15 minute load averages as, you know, red, green, blue time series, which by the way is completely and utterly redundant. I'll let you think about why that's true. So this is kind of stupid. And it's no more informative really than watching a similar kind of ticker chart on Wall Street. You don't play the stock market by watching ticker charts, at least not successfully. Every analyst knows that. So I claim that watching this kind of stuff as a time series is not particularly helpful. You know, sure, I can see some spikes and so on and so forth. It's not that time series are no good, but they're not particularly helpful. It may be a very early starting point, but that's about it. Of course, today we have browser-based dashboards. A friend of mine wrote a paper called Death of Dashboards, which is worth reading. Here we now have the famous black background where I can hardly tell what the hell is going on at all. So this leads me into the idea about performance visualization, which John already touched on. He says things in different ways. I tend to think about these things rather more analytically, but I think you'll see the common ground here as I proceed. So to me, if I restate some of the things that John was just talking about, the central challenge is to find the best cognitive impedance match between two computers. The digital computer system, network, whatever, that you're interested in, and this guy, the cognitive processor. And we want to get the best impedance match, optimize the impedance match between those two computer systems. That's what it's really all about. Not the data, but finding out the information. This is the thing that's going to find out the information. The trouble is, we don't know how this cognitive circuitry works yet. In fact, there's a number of very big projects going on in the world right now. They're getting lots of money. I don't have too much confidence in how much they're going to produce, but we don't understand cognitive circuitry very well at all. We understand a few pieces, like something about the visual system and so forth. Like, for example, vision really begins in the retina. It doesn't start in the brain. The visual cortex is at the back of your head, but the actual vision process begins in the retina. That's where things like edges are detected and so on. And then that information is actually time sliced in the retina electrically and sent back to the visual processor here at the back of your head, kind of analogous, in a way analogous to movie frames, which is rather interesting. But that's kind of the extent of it as far as cognitive processing circuitry is concerned. The issue for performance analysis is even worse because we have essentially n arbitrary metrics that you might like to understand the correlations between, for example. And this becomes very difficult because we've got this huge dimensionality to deal with. I mean, so what we need to do is try to reduce those dimensions in some way without losing the critical information. And also, you have to keep in mind that the brain can be fooled. John mentioned some interesting ones about aircraft detection and false alarms and so on and so forth. You have to keep this in mind all the time. The brain can be fooled. And the way to, I think the thing to keep in mind and understand how this happens is that all cognition is computation. When I say this computer, I really mean it. We don't know how it works. It's not a Turing machine in the usual sense, but it's a computer of some kind. And all cognition is computation. For example, I'll give you a good example of colour. Colour is computed. There's no such thing as colour. It's only in here, and it's computed. And the way to think about it is the brain operates, whatever this computational mechanism is that we don't understand, it operates as though it were a differential analyzer. That means it doesn't understand absolutes. And that's why when you have colours together, they can appear different depending on which colours are surrounding a given colour. So something looks red, may look a certain shade of red if it's got a pink background or something, but if you change it to a yellow background, the shades will alter. So that's because it gets recalculated. And is calculating it as a set of differences, not absolutes. There is no absolute colour. And same thing with the size of the moon. About the moon looking larger than the horizon, then going smaller to the zenith. You know all about that, right? But if you take a photograph of the moon on the horizon, it'll look the same size as the zenith. So what the hell happened there? Well, it happened in here. So this brings me to these Gothic graphs. To me, this is, and I think to the whole world, but there's decades of research on this stuff. You don't even have to rethink it. Just go and read what's been written. There's decades of research that indicate this kind of thing is bad, bad, bad for the poor old cognitive processor. Because the contrast, what's called the luminance contrast, is far too high. The difference between the colours and the background is far too high. Apart from the fact that I can hardly read the text, and by the way, I still don't know what's being represented on the y-axis. There's a whole science of colour. If you're making tools of this kind, please go and read about that stuff. You don't even have to invent it yourself. But it's very interesting, and you'll be very surprised at some of the results. And it's also a window into how the brain works in a very, very surprising way. So just to show you what I mean, I've done this in R because that's what Jason asked me to do for tomorrow. I do sling a fair bit of R. So just as a matter of convenience, I'm showing you here, if we have this is a plot that I've done in R. It's a time series because the index on the x-axis happens to be time. It's showing some kind of scalability. On the y-axis, we're looking at logical IOs per second. That's a throughput, so that's one of those metrics I talked about, so I think I understand what that means. We've basically got time on the x-axis, and then there's 4 sets of measurements shown on the same plot. And if I just do this by default, and this is the kind of thing I get, which by the way is not particularly good. But at least I can sort of differentiate it. Now if I'd like to try and tune that up with this cognitive processor, putting a black background certainly increases the luminance contrast, but I've lost the legend now. So this could be bad news if you're trying to figure out exactly what's going on. It's not a matter of looking at fancy graphs, it's a matter of trying to understand what is the graph trying to tell me, what is the information in the graph, or the plot. If I put a grey background, I need a more neutral background to lower that contrast luminance. Grey is the standard colour. Pale green is also very good for reading, but reading text, not plots. But I'd be happier with that. The trouble is that pale green wouldn't work here because we've got green already. So in R, there's now a package which helps you to take the next step, which is to keep the grey background, but to adjust the colour luminance contrast by choosing more subtle colours for the actual plots than just plain pastel shades, RGB values. So there's a package that actually helps you do that automatically. So we can argue all day about whether this is the best representation. The point is I just want to show you some of the different representations, and that there are packages in R, for example, to help you to improve the impedance match to the cognitive processor. Getting back to time series are okay. They're a good starting point, and if you can see where spikes are, and in particular if I can look at stacked graphs or even a dashboard from that point of view, but if things are aligned correctly, then I can see where the spikes occur and line them up, and I'm showing here different metrics, but on the same time base in each case. That helps me to perhaps determine something about what's going on, or at least the next step to take in the analysis process. But it can get much more interesting than that. So the point I'm showing on this slide is that the data doesn't tell all. Here you see a server, I won't say which company it's from, but you can see this is for a 24-hour period roughly, and this server, a back-end server in a large major website, is basically saturated most of the day. And that's what the data tells you, because we're looking here at CPU utilization, and utilization is bounded between 0 and 100%, end of story. But you can do things if you understand how to take the next step, which is visualize, and the next thing is analyze, using tools like R. What I did was I was able to show this particular client what the actual effective load on the system looked like on top of the actual data, because the data doesn't show you this kind of thing. So what I'm showing you here is that the data here is limited to 100% utilization, because that's how it's defined. What I'm showing here is an effective utilization, the blue curve, which is, say, peaks at about roughly 150%. What does that mean? It means that even though this box is running saturated during the day, you're already chewing up 50% of a server you haven't even written the PO for yet. And if you wait much longer, by the time you do figure that out, write the PO, have it built, have it installed, it will saturate too, and you will have completely wasted your money. So this is a kind of a look ahead, but you can only do this kind of thing by going from the visualize to the analyze step. And that's what I think most of these tools should be doing. In R, there's many different ways of displaying static graphs. You can also do animations and so forth, but this is the typical static kinds of graphs. There are many different kinds of plot packages out there. These really are coming from the mathematical statisticians, what's called exploratory data analysis, which is typically static representation of data, but just shows you some of the kind of choices that are out there, all of which can be very helpful depending on what you're trying to do. So you can choose your Z poison depending on what you're trying to do with the data, what you're trying to get out of it. You can also enhance the plots. Once again, here I'm showing the data as data points together with confidence intervals. The other key point here is that it's on a grey neutral background to help that luminous contrast. Going a little bit further, there's other kinds of stylistic representations of data. This is somewhat overlapping with what John's point about different kinds of alarms, alerts, what the data trying to tell you, and whether you should ignore it or not. And then he ended up talking about essentially a virtual assistant to do that kind of thing. Well, in terms of this cognitive processor, if you could make each metric that you're looking at an attribute on a face, such as this, which is, there's nothing new here, this is called a turn-off face, which has been around for decades. The smiley face means everything's cool, and then if you see an eyebrow lifted, it's like, well, what? And then if you're going to add audio to that, talk to me, tell me something, what do you think? This would be a good way to go, right? So I'm just saying some of these packages already exist, so that part of the technology has already been done. It would be nice to meld some of that with some of what John was talking about. And by the way, just to show you down here, these are kind of almost one-liners in R. These packages are so highly developed that a lot of it's just kind of one-liners to get to where you want to be, which is quite nice. It's well worth learning just from that point of view alone. Other kinds of representations of performance metrics, Kvyat charts or radar charts. This is just showing you the kind of thing you can do in R. The main point here is this dimensional reduction. So even though you perhaps can't read this, we could certainly zoom in. This is showing you, like a gazillion metrics radiating around this circumference, and this is just a way of compactifying many dimensions into one. There are many other techniques for doing this. And by the way, you should have your own choice as to which things you prefer. Otherwise, all our brains are different, so you should be able to choose which ones you prefer. And which, if you're colourblind, then obviously colour is not going to work well for you. Tree maps, these things are just packages already available. I just wanted to show you that these things exist. This is a way of addressing the question. I've got this data centre with a couple of thousand servers. How do I know which ones to look at? Well, it's called divide and conquer. Most of them are probably not doing much. And maybe that's the way it should be. I don't know. We need to know more about it. But this would be a quick way of getting a representation of showing which are the heavy hitters versus which are the ones that are basically doing nothing. Here I'm just showing website locations, but you can imagine that could also be CPU utilization in the data center. I've actually done that. And here's one of the results that I did. This is showing a little bit different theme. This is a kind of a heat map. So on the bottom here, I'm showing you 10 or so, a dozen different servers, the critical ones, which we might have determined from the tree map. So these are the heavy hitters, let's say. And then the time axis here is going in the Y direction and upward, positive. And the point about this is then I can look to see which ones are running hottest. And I can also see in time, across this way, for example, this one may have been doing some processing, and then that had actually communicated with the server over here. At a later time, it starts to run hot because of something that happened back here. So I can coordinate the thing in time, potentially. And I can see this very quickly in a very visual way, and then I should be able to sort of drill down and deep dive into what's going on. And there the data comes to the fore again. I want to know also, not just visuals, I want to know at some point I want to be able to drill down and get that numerical data to make the actual numerical comparisons and see what's going on. Here's some other stuff that I've done over the years. This is another way of doing CPU utilization. I actually have some animations for this, which I can show you later if you're interested. This is looks a little bit unusual. This is just showing CPU utilization on what's called a barocentric coordinate system. And so basically, if things are running well, they sort of should be located more or less up here. Ideally up here at the apex. This is showing user time, maximum user time in this direction, maximum system time in this direction, maximum idle time in this direction. So you'd like things to be up here normally, but then on the other hand, you've got to do I/O, so there's going to be some stuff occurring over here. And in fact, this is, I don't think the system had about 100 CPUs on it, so this is showing 100 CPUs at once as a snapshot, but there's an animation. You see the time counter there. This thing is just one frame out of a movie. And interesting enough, you see it starts over here idle, right? Then we start with this benchmark workload, and you see it ramp up to this point, this area up here. But notice also there are 3 dots over here. Those 3 dots represent 3 CPUs that are dedicated just to doing I/O for the purposes of the benchmark. In fact, that is the right way to configure the system, it turns out. And you can see that immediately without even looking at the numbers. And then you can also see how they move as a cloud of points and separate in time as an animation. So time series can be replaced by animation. That's one of the key things I'm trying to get across this morning. And then you can also do this in 3 dimensions. Here the idea is you would grab hold of this tetrahedron and you can swing it around in a virtual 3 space, because if you look at it in a certain axis, you can see that the points just look like a jumble of points. But if I can turn it around and look on this axis, you see it separates into 3 clouds. That must be telling me something. There's some kind of periodicity in there. What's causing that? What does it mean? Now we're talking about information. This idea, by the way, goes back to the early 1970s from John Tukey, who was also at MIT originally, I think, with Richard Feynman, and then he went to Princeton. So in my book, Tukey trumps Tufte. Tufte is what I call the data artist. Tukey is a data scientist. And the point is that I can take John Tukey's ideas. In fact, this is done in mathematics. I take John Tukey's ideas by simply reading about them and implement them and actually start doing something with it. With Tufte, it's like, well, that looks nice, but I've got this other kind of data. So what would Tufte do? Hello? So for tomorrow, some possible hacks. So R has its origins back in Bell Labs, kind of like Unix. In fact, there's almost a sort of a parallel history in a way. It derives from a language called S that was developed at Bell Labs. It's had several renditions, 1975, 1980. Latest one was 1988. That's the version of R that we see today. It's a scripting language. It's an interpreted language, which is very nice for putting things together quickly. I love interpreted languages. I don't like fighting compilers. One of the downsides it shows its age is that the console interface that it has, if you look at that generically, you see expressions like this. So it can take mathematical expressions and then calculate a value for it. If I compare that with Mathematica, for example, it has a completely different paradigm, because it was first started in around about 1988, was the first commercial release of Mathematica. It came with much newer ideas. One of the key ideas is that data analysis of this type can be represented as a document interface. I'm not saying that's the best interface, but that's a very interesting idea. So as you're analysing and putting things in place and doing calculations and bringing in more data and massaging the data and so on and so forth, you're producing a document, which where you can also put text, and that's extremely good for embedding your intent of your analysis, which is very hard to capture in any other way. Same thing with programming languages. Don Knuth had been on about this for a long time. Well, actually, the whole idea was really implemented quite well at Xerox PARC, where I spent a decade or so. And the idea is that when we wrote a computer program in a language called Mesa that was developed at Xerox, the way you did it, the way you think of it today, is that it looked like a Word document, but it's a computable document. So when you throw it into the compiler doesn't read the text, it reads the parts that are to be compiled. It knows about that because of the way the thing is set up with the appropriate fonts and all the rest of it. So Mathematica has kind of leveraged that sort of idea, and also, of course, it has the ability to show the mathematical equation in the correct font, so it's easy for this cognitive process to read it if you know the math, if you know the Greek. This is extremely ugly. So R suffers from not having fonts, no symbolic computation, of course. But what has been developed in recent times are better IDEs, such as RStudio, browser-based interaction through something called Shiny, and then there are a number of other developments, including using R with Hadoop. This is the big data game, of course, that you've heard a lot about, and that's also pushing the envelope on R. One of the issues is that R interpreter, of course, is single-threaded. That could be changed, but nobody's done it yet. And also, to do some serious work, you need a full app stack, basically, to connect with the R engine. And a company called Revolution Analytics is kind of in this space at the moment, trying to do some of these things and then somehow leverage some of that commercially, a little bit like a Red Hat type of business model. So there's plenty of room to be innovative, not at the bottom, at the top, actually. So in terms of tomorrow, some ideas would be coupling simple statistical analysis to monitor data, your favourite data, to display the error bars that I mentioned in the first slide, playing with alternative kinds of backgrounds and luminous contrast in tools like graphite that seem to have this black background by default. Apply the colour brewer to get more subtle colour variations that are helpful to the brain, and apply the effective capacity curve that I showed you a few slides back, where I was showing you the 150% effective utilisation of the server that you haven't bought yet, and replacing strip charts with animation, which is, let's do movies, let's knock off with strip charts. And the other thing I want to end with by saying that common sense is the pitfall of all performance analysis. So there's something from a thought leader, which I'm not. So I'm just going to end now, but I didn't talk about modelling because I don't think we're going to do much of that here. There's not the time in this conference, and that's not the purpose that Jason had in mind. But I can't resist. Recently on Twitter, I became aware of some work that was done at RedMonk, and somebody there was doing some analysis of when GitHub would hit 4 and 5 million users respectively. And I looked at that for a while, and I thought, so the way they arrived at these numbers was they did what's called a log linear plot. That's sort of where they ended up. So that's a logarithmic scale on the y-axis, linear on the y-axis. These are actually time periods that correspond to years or months out from now. And what I recognised was this: the guy who did this analysis missed something. If you actually put it on what's called a log-log plot, and if the data lines up in a straight line, this tells you there's a certain kind of modern operation called a power law, which most people don't know about. But this boomed in physics in the 1970s, so I know a fair bit about this stuff. And so I threw this log-log stuff at it, and here you see the result, and then I did my computation. So He's claiming 4 million by August 2013. Jason can tell us where you are. I don't know. 5 million in December. That's the end of the year. I think it's going to be a bit later than that based on my log model. So we can take bets on the side and at the pub tonight. You know where my pockets are. So thank you for your attention, and I look forward to discussing these things offline with you, and some ideas for tomorrow, and I look forward to the hackathon workshop tomorrow. Let's do it.